Lo mismo, 20-25 minutos.
Okay. Good morning, everyone. My name is Alvaro Martinez. My thesis supervisor is Ramon Canal, and my thesis is well, about the memory architecture. I chose the most promising three technologies for replacing. The idea was to evaluate memories to replace main memory, okay, the RAM-based main memory. So I chose STT-RAM, resistive RAM, and phase-change memory. Okay. This is the outline of my presentation. First, I will introduce a motivation, the main contribution of this thesis, the framework I used to simulate this work, which is called M.Phil, Non-volatile simulator, the experimental methodology, and then I will describe quickly the three candidates, okay, the STT-RAM, resistive RAM, and phase-change memory. We will see a comparison of all these three memories, and together with the RAM, and finally I will do some conclusions, okay. So the memory wall. We know that current microprocessors are constrained by three walls: the IRP wall, the power wall, and the memory wall. The memory wall, basically, okay, we now have Moore's law still applies, so we have more and more transistors on each chip, and this comes in the flavor of several cores on the same chip. This cores, of course, give more performance, more peak performance, but we have to feed these cores with operands. Okay, so today a microprocessor can have 1 teraflop in double precision. So this means that we need to feed around 16 terabytes per second, which is a lot of information. So the solution so far has been to provide even deeper and deeper levels of cache memory, but this not works for the whole set of programs, only for those that have very good temporal and spatial locality, and this cache hierarchy occupies area that otherwise could be used for computing, and also, of course, the cache memory has power issues, right? Another solution is to add more pins in the chip, but this has the disadvantage that the manufacturing cost of the chip is higher. The complexity of the manufacturing process is higher, and the final cost of the chip increases. Another solution that is taking some manufacturers like IBM with the Power PC, the Power 7, is to stack one last level cache implemented in DRAM on top of the chip. Right? This is called embedded RAM or stacked RAM, but according to this institution, International Technology Roadmap Semiconductors, there are problems in scaling DRAM beyond 20 nanometers. The solutions to DRAM are unknown because cost, reliability, and power issues. Talking about power, in a current HPC center, 40% of the power budget is only due to the memory subsystem, which is a lot. For example, I have here an example that currently in a current microprocessor doing a fuse multiply addition instruction consumes 100 picojoules versus 2000 picojoules of reading the operands from the RAM. So with current trends, even in 2018, with a modest bandwidth of 0.2 bytes per flop, which is very low, the cost of reading operands from memory is 2000 bytes. Okay. So the conclusion of this is that new memory technologies must be investigated. Right? And in this thesis, I have studied the three most promising technologies, non-volatile technologies. Okay. The main contribution of this thesis is, out there are a lot of papers that each one describes these three technologies separately, but on different frameworks, right? So we don't have a fair manner of comparing each technology. So what I have done is to use a novel simulator that has been published the last June, okay, that and evaluate the three technologies on the same simulator. This simulator, MVC, outputs, the main metrics are read-write latencies, read-write power, work energy, area, and leakage power. Issues that are not covered in this work are things like reliability, which is very important, and also things like write endurance, the number of writes that your chip is gonna live, right? Also, there are of course more candidates to replace the RAM, like ferroelectric RAM, carbon nanotubes, molecular memory, and so on, but these are not evaluated. I will continue with a description of the simulator. MVC is a system-based simulator, and it has two modes of usage. Say that you have a chip, you have in mind an architecture with the number of banks, the number of sub-banks, the internal routing and so on, and you want to estimate the power, the latencies and so on of your chip, so you put your chip specifications in the simulator and you get the result, the metrics. The other one in red is the one I used, is you tell MVC an optimization target, you put the minimum number of metrics in order to work this simulator, and let the simulator to search for the whole space, search space of all combinations that meet this optimization target. Okay, the optimization target can be read latency, write latency, read energy, write energy, leakage power, or area. Okay. Okay, in order to use sensibly the simulator and do fair comparisons, I have departed from two sources. First, there are actual chips implemented in these technologies. There are papers with some specifications of these chips, and also there are some scaling rules from main manufacturers and academia like this institution. And the three technologies has been projected, evaluated for the following, 2011 was when I started the thesis, and for the following years. The important thing here is that I haven't evaluated its technology in ISO process, but its technology is contemporary to each other as predicted by the main manufacturers. So for example here, we have that in 2015, the RAM is expected to be 25 nanometers, STT-RAM 25 as well, and phase change memory 28. Okay, let's continue describing these memories. Okay, STT-RAM is based on magnetic RAM. We know this logo, right? This is a very old cell of magnetic RAM. Okay. In this kind of memory, the binary information is encoded as a magnetic field in a ferromagnetic material. Okay, this technology was abandoned in this time because of the introduction of the microchip and CMOS memories. But it has seen a renewed interest thanks to the discovery of the magnetic tunnel junction. Okay, this means, well, the principles of operation is we have basically we have 3 layers. 2 layers are made of this magnetic material, and in the center there is a layer of an insulator. But the 2 magnetic materials can have either the spins of the electrons up or down. If the spins of the two layers, of the 2 magnetic layers, are aligned, then the cell presents low resistivity. If the spins are on opposite directions, the resistivity is high, so it doesn't allow to pass current. Of course, ones and zeros can be encoded as parallel, well, this is called parallel or anti-parallel configurations. We can read data either by injecting a current in the cell and sensing the voltage decay, or vice versa. We can establish a voltage and sense the resulting current. This is how STT-RAM cell works. The same applies for STT-RAM, but we have a fixed layer in which the spins are fixed, we cannot change it, and a free layer in which the spins are free to change of polarity. Resistive RAM is a novel technology that is based on a recent discovery by Hewlett-Packard of a circuit element which they call main restore. Okay, this element was predicted in the 60s, but it was discovered in 2008. A main restore is basically a resistance whose value depends on the history of the current that has passed through in the past. So at any instant in time, it's a resistance with units is the ohms, like an ordinary resistance, but we can change the value of the resistance by injecting current. This technology allows to store multiple bits per cell, because we can store, say, we can put the main restore in several levels of resistance. Still, this is challenging because we don't have too many prototypes out there. So far, the best is a 4 megabits memory, so it's not very. It's very difficult to predict how it's going to evolve, but it's a very promising technology. It's a technology according to Hewlett-Packard. This technology has the advantage that due to the separation between the high resistivity state and the low resistivity state, we can get rid of the typical access device, which is typically a transistor, and form crossbar structures without any access device. So we achieve the minimum cell size possible, which is 4F squared. Finally, phase-change memory. It's based on the property of some materials that they have 2 phases. This material can be crystalline or can be amorphous. If this material is crystalline, it presents low resistivity. If the material is amorphous, it presents high resistivity. We can change between crystalline and amorphous by applying heat. If we are in a crystalline state and we applied current, we know that applying a current dissipates heat, and the material is heated up to 660 degrees, and the material becomes amorphous. It corresponds to this curve. If we are in a crystalline state, amorphous state, and we want to make it crystalline, then we apply a pulse right this one. But hold on, if the conductivity is null, how can we inject current? Okay, the key to these materials is that it presents a threshold switching, in which if you apply the voltage up to a threshold, this material presents a sudden pulse of intensity. So the temperature rises up, and the material starts to conduct. Then you don't have to heat it up to the maximum temperature, only to 300 degrees, and nail it back. Because we have to inject high currents, maybe we may replace the MOS transistor, the access transistor, by a bipolar transistor that allows to inject more current without area penalties. And also, phase change memory can be engineered to store multiple bits per cell as resistive RAM. And this is the most mature technology. Even commercial chips are now available. Okay, this is the overall comparison. This is a lot of information for a single slide. But basically, okay, the report has more details, but we can infer from here that this is the area in millimeters squared. We can infer that the general trend is that, okay, this is the first set of bars, is the resistive RAMs, this resistive RAM. This is the magnetic RAM, STT-RAM, and this is phase change memory, and this is DRAM. Okay. So the general trend is that the information density is higher and higher when we advance in the following years. Okay. What about latencies? Well, latencies is the weakest point of these kind of memories. We see here the RAM, and these are the non-volatile memories. But in 25 nanometers, if we optimize, for example, resistive RAM for latency, we are close to the RAM, 223 versus 211. Okay, this is wide latency. We see that the phase change memory has the highest wide latency because we have to warm up the material, and this takes time. The energies are the best thing of these memories. We see the contrast between the non-volatile candidates versus the RAM. Okay, we see a lot of advantages in terms of energy. Well, for phase change memory, since it's based on heat, the energy is the highest among the three candidates. But in the future, it is expected that even phase change memory will consume less energy than DRAM. Leakage. Okay, DRAM is a leaky technology per se. We have to refresh the RAM because the charge stored in the capacitor, the charge leaks through the access device. But these technologies are non-volatile, so we can gate off the current, and it doesn't lose the information. The only leakage appears on the external circuitry, right? But not in the cells per se. Okay, summary. Well, this is more or less what I have said, right? Non-volatile memories shows clear advantages in terms of power consumption and area, and also leakage. They don't have to be refreshed, and this is important. All the three technologies are CMOS compatible, which means that we can integrate these technologies on CMOS-based processors. Okay, my opinion, some authors claim for the search for a universal memory that in the end will replace the RAM, but this is not my point. Why? Because we are entering an era of heterogeneous computing, where we will have on a single chip several cores with different trade-offs, basically performance energy trade-offs. So why not to integrate different memories to different cores based on these trade-offs? Why memory should be an exception in this heterogeneous world? And also, DRAM is a very well mature technology that has worked very well for 30 years, and we cannot get rid of it now. Okay, future work of this work. We are introducing even more variables to the computer architecture space, right, the landscape, and this introduces even more questions, right? How much and what type of memory should each core include? I don't know. Shall this memory operate like a scratchpad memory managed by the programmer, or they will be like hardware managed caches? Shall the operating system be aware of this heterogeneous memory system? How to fit all these technologies in a cost and reliable way in a single chip? I said about data reliability and data retention that was already this work. And also, one utility of these non-volatile memories is that it could be useful for checkpointing in big data centers. Imagine that the electricity goes down. You have saved the state of the server in the non-volatile memory, so it can stay the information there until the electricity goes up again, and you can restore the computation. And this is all I have. So thank you. Any question?
Sí, paso en español.
Vale.
No tienes problema. A ver, pocas preguntas. Una de muy concreto de una duda que me ha salido en la presentación. En la primera gráfica, cuando hablas de latency, dices que, bueno, comentabas que
sí,
hay una que muestra una latencia muy similar a la de DRAM. Pero cuando estaba mirando en la gráfica, o entiendo mal yo la gráfica, o no lo he visto bien, la que tú dices que tiene una latencia de 2.30 con respecto a la de DRAM que tiene 2.11, ¿no es lo mismo? ¿No es DRAM pero con distintas áreas?
Creo que es en rate latency, ¿verdad?
Read latency, es que me daba la sensación que era DRAM pero en distintos grupos de barras. En la derecha de todo, la última barra es 2.11, que es DRAM, sí, ¿correcto?
Sí.
Y en el segundo, que es con una mayor escala de área.
Exacto. En el eje X tenemos las proyecciones del escalado de las memorias para los próximos años.
Y cuando comentaste que mostraba un rendimiento similar a la de DRAM, ¿a cuál te referías? Porque entendí que era...
Ah, vale. Vale, claro, o sea, cada barra de aquí, ¿vale? Hay varias barras, cada grupo de barras representa una tecnología, ¿vale?
Sí, sí,
Se ve
sí.
pequeñito, memory store, ¿vale? Y cada barra dentro de cada grupo representa un optimization target, ¿vale? Entonces, por ejemplo, estas dos pequeñitas de aquí quiere decir que el optimization target es read latency. Entonces, si optimizamos nuestro chip para la latencia de lectura, entonces estamos cerca a la DRAM.
Vale.
No sé si es eso.
Sí, sí, es que no había visto esos dos.
Sí, es que se ve muy pequeñito.
Vale. Vale, de acuerdo. ¿De Future Work ya habéis empezado algo en concreto?
No, porque mi intención era continuar con el doctorado, pero bueno, me contrataron en Intel y de momento me gustaría algún día, pero de momento pues no. Es un tema interesante, ¿no? Continuar en este sentido, porque la memoria, pues, en computación estamos moviendo datos continuamente Y la memoria es lo que actualmente, aparte del power, nos limita, ¿no? A la hora de alcanzar el performance máximo que te ofrece el procesador.
Vale, y... bueno, en principio eso era...
Vale. Yo también tengo mi poquita cosa. Es una lástima que no sigas este trabajo ahora. Promete con una buena tesis. Y aunque se esté trabajando en Intel, yo creo que se puede, ¿no?
Pues depende
de cambiar de proyecto.
No, pero no tienes por qué estar 200 horas semanales, ¿no? Bueno, anyway. Yo quisiera saber por qué te has... ¿cuál ha sido la razón de analizar estos tres tipos de memoria y no, por ejemplo, nanotubos de carbono o otro tipo? Y lo digo porque el final de la ley de Moore tampoco está tan lejos, ¿no? Y estos tipos de memoria no sobrevivirán a eso, y a lo mejor los nanotubos de carbono o algo parecido sí. Entonces, supongo que habréis tenido alguna razón para enfocaros en estos y no en otros.
Sí, varias razones. En primer lugar, porque estas es donde más documentación fiable hay. Carbon nanotubes, pues a lo mejor, no sé, a lo mejor hay memorias que, pues eso, hacen 4 bits porque se basan en fibras de carbono, ¿no? Que se tocan o se separan. Entonces, no creo que haya muchos datos a partir de los cuales sacar una buena tesis extensa, ¿no? En segundo lugar, este tipo de memorias son compatibles con SIMOS, ¿vale? Yo no sé si la ley de Moore está lejos o no, pero cada 2 años el número de gente que dice que está a punto de acabar se duplica, pero la cuestión es que se dijo que se acabaría y todavía ha continuado. Entonces, no sé, yo creo que este tipo de memorias, como hemos visto, ofrece muchas ventajas, y no solo para memoria principal, sino, por ejemplo, para los pendrives, que están basados en flash memory, ya es muy difícil escalarlos. Entonces, este tipo de memorias, phase change memory, ofrece muchas ventajas. Es una tecnología muy prometedora para reemplazar a los pendrives. Entonces, no sé, esos son los motivos. Al principio, yo cuando empecé esta master thesis, pues leí de todo un poco y el trabajo se fue estrechando hasta dar con estas tres.
Vale. Muchas gracias. Pues pasaremos a la